Hi, I'm TuanaS and this is my optical current sensor term project. In this project, the purpose is to measure the photodiode current, which is usually really small, and we want to measure it under three conditions: lab light, daylight, flashlight, and dark conditions. As I mentioned before, the current is really small, so we need some methods to be able to measure it. In the first part, we're gonna use a transimpedance amplifier. We're gonna measure the output voltage with a multimeter directly and divide it to the resistance, and we're gonna obtain the photodiode current. In the second part, we are going to use an integrator which lets the current accumulate over the capacitor. So this way again we can measure small currents, and in that part we're going to use an oscilloscope because we have a changing output. We're going to calculate the slope of the output voltage and multiply it by the capacitance, and it will give us the photodiode current. This is my circuit setup. I'm going to show my connections first. Here you can see that my supplies are -12, around -12, +12 voltages. And here I'm supplying the op-amp. I have my photodiode, which is a red LED. In the circuit, it is behaving as a photodiode. I have my supply bypass capacitors to reduce the noise. I also have short cables to have less noise. Because they add a lot of noise to the circuit if they're too long. And here's my feedback resistor, which is around 10.16 mega ohms. And here's my multimeter. I'm gonna measure the output voltage under three different conditions. At first, I'm gonna start with the lab light. Right now, lab light, which is daylight, I'm gonna measure the output voltage. Here I'm finding the output here. It's around 0.04, 0.039, let's say 0.04. And we're going to divide it by the resistance. So in the under the first condition, daylight, we obtained around 3.94 nanoamperes of photodiode current. Now we're gonna continue with our second condition, which is flashlight. And now I'm gonna measure the output voltage again. I'm waiting for it to be stable. It's around 0.44, and I'm gonna divide it by the resistance. I calculated the result as around 43 nanoamperes, which is a lot bigger than the daylight one, which makes sense since the more electrons were emitted on photodiode because there was more light. For the last condition, I'm getting help from my friend. We used a black fabric to cover the photodiode, and now I'm gonna measure the output voltage again under these conditions. It gave us a negative voltage, which makes sense because there's some offset voltage. So I'm gonna divide it by the resistance and try to understand our calculations. To be able to measure the offset voltage, I constructed a basic circuit, an amplifier circuit. I used around 10K resistor, and I had my feedback resistor from the previous setup. Here the gain is around 1042. So I'm gonna measure my output voltage and divide it by this gain to find my offset. And I'm measuring it. Measuring the output voltage. Mine is 3.166. And when divided to the gain, it will give us around minus 3 millivolt offset voltage. So we will recalculate our previous calculations to have more correct results. Now I will explain the second part of this project. Here, instead of a resistor in the feedback loop, we use a capacitor, making this circuit an integrator. The purpose is to let the current accumulate on the capacitor so that we can measure small currents more efficiently. Here, also, we don't use a multimeter to measure the output voltage anymore. We use an oscilloscope so we can see the ramp and calculate the slope and multiply it with the capacitance to calculate our photodiode current. Now I will show my circuit connections. Here, I'm giving minus 12 plus 12 supply voltages through this machine, and these are my connections. The feedback loop is here. This is my 1 nanofarad capacitance. Now it's shorted because the initial voltage should be 0, and then we're gonna take it off and trigger the circuit. My probe is connected to the oscilloscope. Now I will repeat the experiment under 3 conditions: daylight, lab light, flashlight, and dark condition. At first I start with the daylight condition. Here I used a shorting wire to short my capacitor, and here we can see that the output is almost 0 voltage. Here we see a 10 times multiplied version since I used attenuation 10 times. So it's around 2.7, minus 2.7 millivolts, which is almost 0 voltage. So our circuit behaves well. And now I will trigger the circuit by removing the shorting wire, and then we'll see a ramp. Now I prepared my setup. My time division is 1 second per div. My voltage division is 10 voltage because I have 10 attenuation. Now I'm gonna put single seconds button and wait for it to say ready, and then I'm gonna pull off my shorting wire. Here I'm pressing on it. It says armed. I'm waiting. Ready. Now it's triggered, and we'll wait to see the ramp output. And here we are. This is the slope, and through the slope we're gonna measure the current, photodiode current. Here I changed my volt per division to be able to understand the slope better, and I calculated as around 5 voltage divided by 1.4 seconds, which actually gave me around 3.3 nanoamperes as a result. Now I will repeat the same experiment with flashlight on. I put my shorting wire again so that my initial condition is 0. And now I'm gonna set the time per division to 1 second per division and adjust my trigger settings, and then I'm gonna trigger the circuit again. I pushed the single sec button. Now I'm waiting for it to be ready. It's ready. Now I'm pulling off the shorting wire, and now it's triggered, and we'll wait. And the slope is obviously very steep, very high, because now we had our flashlight on. A lot of current is passing through. I changed the time division and voltage division settings so I can understand the slope better. Here is the ramp we got from the flashlight. Here I can see that my slope is 5 divided by around 0.2 seconds. So I get 25 nanoamperes from this experiment, this condition. Now we're We're gonna do the third condition, which is dark condition. I got help from my friend for this, and the LED is, which is actually photodiode in this experiment, is covered with a black t-shirt fabric. And now I put my shorting wire again. Now we're gonna trigger the circuit again to have our ramp. Now I pushed my single sequence button. It says ready. I'm pulling off the shorting wire. And we're gonna wait. And yes, here we are. I changed my voltage division and time division to understand what the slope is, and here we see 1.2 voltage rise, and it happens in 6.4 seconds, and from this we get around 0.18 nanoamperes. But we never considered the fact that there's an input bias current. We assumed it's zero. So our photodiode currents aren't actually what we calculated. We have to calculate the input bias current and subtract it from our previous measurements to have a better result. For this purpose, I'm gonna remove the photodiode or LED, and now we're only gonna have input current coming from the op-amp. And I'm gonna short the capacitor again and repeat the same experiment to again calculate the slope and multiply it by the capacitance. Now we came to the last part of the project, the last part of the experiment. Through these conditions, we never considered the fact that there's an input bias current of the op-amp. We're gonna calculate that, and we're gonna subtract it from our previous results, so we have more correct calculations. To be able to calculate the input bias current, I simply removed the photodiode, so the only current going through the capacitor is the input bias current of the op-amp. And now I'm gonna actually repeat the same measurement. We're gonna get a ramp, and we're gonna find the slope of it, and then we're gonna multiply it by the capacitance. Now I push the single seconds button. Now we're waiting for it to be ready. Now I'm removing my shorting wire, and we're waiting. Okay, now I'm gonna change my division settings, and we're gonna calculate the slope. I calculated my slope. The voltage rise is around 0.1 volts, and the time it took to rise to that point is 10 seconds. So we obtain around 10 picoamperes input bias current. So we're gonna subtract it from our previous results to have better results, as I said before.